In this video, we're going to look at another example of areas between curves. The question here is find the area of the region bounded by the curves x equals sine of pi over 2y and x equals y squared and y equals 2. The first step is to find the points of intersection of x equals sine of pi y over 2 and x equals y squared. And we do this by letting x equals x and solving for y. So we have sine of pi y over 2 is equal to y squared. Now, we can't solve this algebraically. We can't apply rules of algebra to solve this. So it means we have to make a guess, a good guess. And oftentimes the question has been constructed such that you can just put in numbers and integers and in all likelihood it would work. But of course you have to test it out. So let's put y equals 0. If we put y equals 0 into this equation, we'll get sine of pi over 2 times 0, that's 0, is equal to 0 squared. Well, sine of 0 is 0. 0 squared is 0. That checks out. That means y equals 0 is a y coordinate of point of intersection. So y equals 0, let's substitute this into x equals y squared, and we get x equals 0. So now we have a pair of xy coordinates, 0, 0, as one of the points of intersection. So now let's try y equals 1. If we plug y equals 1 into this equation, we're going to get sine of pi over 2 is equal to 1 squared is 1, and sine of pi over 2 is just 1, so we get 1 equals 1, and that works out. That means y equals 1 is another y coordinate of point of intersection. So let's plug it into x equals sine of pi y over 2, and we get x is equal to sine of pi over 2, which is 1. So we have another pair of intersections, which is 1 and 1. So 1, 1, just to summarize, and 0, 0 are the points of intersection of x equals sine of pi y over 2 and x equals y squared. All right, so the next step is to sketch a region bounded by these two curves and y equals 2. That's been provided for us here. So you can see how the sine graph is, because it's x as a function of y, is basically just oscillating about the y-axis. And x equals y squared is a parabola that opens to the right. So let's look at a differential element. When y is between 2 and 1, so when y is between 2 and 1, you can see that the differential element is going to be the right x value, x right, minus x left. Well, the right x value touches the curve at x equals y squared. The left x value touches the curve at x equals sine of pi y over 2. So the differential area will be y squared minus sine of pi y over 2. Key concept is always more minus less. X right minus x left. In a previous video, when everything was in terms of x, it was y top minus y bottom, or y more minus y less. So it's always more minus less. That way the answer is always going to come out positive because you're adding positive quantities. So that's really the key point, is always decide when you're doing it with horizontal slices, what is the right x value and what is the left x value. And always go x right minus x left. Now, what happens when y is between 0 and 1? When y is between 1 and 0, you can see that the right point of contact is x equals sine of pi y over 2. That's a larger x value. The left point of contact is x equals y squared. So the differential area will be dA is equal to sine of pi y over 2 minus y squared times dy. All right, so now we have to set up a definite integral to find the area. And that's going to be area is equal to 0 to 1, x right, so this is x right, minus x left. Now, when y is between 1 and 2, it switches. Now x right is y squared, x right, and x left is sine of pi y over 2, x left. So let's split up the integrals and solve. Area is equal to integral from 0 to 1 sine of pi y over 2 dy minus integral from 0 to 1 y squared dy plus integral from 1 to 2 y squared dy minus integral from 1 to 2 sine of pi y over 2 dy. Now let's apply U substitution to solve the first integral. So we're going to let u be equal to the inside function pi y over 2. Du, the differential of both sides, will be pi over 2 dy. Solve for dy and we get dy is equal to 2 over pi du. So the first integral will be integral of sine of pi y over 2 is going to be minus cos of pi y over 2, and we divide by the derivative. We're basically reversing the chain rule, so that's essentially dividing by pi over 2, which is the same as multiplying by 2 over pi. And this 2 over pi comes from the U substitution from the fact that dy is 2 over pi du. And this is integrated from 0 to 1, so evaluated, I should say, from 0 to 1 minus. Now, what is antiderivative of y squared? That's going to be y cubed over 3 from 0 to 1, evaluated from 0 to 1, plus antiderivative of y squared, again, is y cubed over 3, evaluated from 1 to 2, minus an integral sine of pi y over 2. We already did that with the substitution method, so that's going to be minus cosine of pi y over 2 times 2 over pi. Double negative is positive, so let me make it positive here, times cos of pi y over 2 times 2 over pi, evaluated from 1 to 2. Okay, let's apply fundamental theorem of calculus and solve this. Area is equal to, let's factorize minus 2 over pi, bring that outside the brackets, and we have cosine of pi over 2 because we're plugging in y equals 1 into here. So cos of pi over 2 minus cosine 0, putting the lower limit in, minus, now I'll put 1 in, 1 cubed over 3, that's 1/3. Put 0 in, that's just 0, plus y cubed over 3, that's going to be 2 cubed over 3, that's 8 over 3, minus 1/3, and let's write the remainder on this line, plus 2 over pi times cosine of 2 times pi over 2, that's going to be cos of pi, minus cos of pi over 2. Now it's very important that you memorize these results for cosine and sine. Cosine, in this case, we just have cosine. Cosine of pi over 2 is 0. That's cosine of 90 degrees is 0. Cos of 0 is 1. And cos of pi over 2 again is 0. Cos of pi, that's cosine of 180 degrees, that's negative 1. If we simplify all of this, we're going to get area is equal to minus 2 over pi times 0 minus 1, minus 1/3 plus 8/3 minus 1/3 plus 2 over pi times negative 1 minus 0. And if we simplify this further, we're going to get area is equal to minus 2 over pi times minus 1, that's 2 over pi. Then we have 8/3 minus 1/3 is 7/3 minus 1/3, that's 6/3, so that's going to be plus 6 over 3, that's 2, minus 2 over pi. Now 2 over pi cancels, and the result is 2. This is the area under the curve, the shaded area. If we go back to the previous page, we just found this shaded area. So we found all of this. And all of this. The hard part is setting it up, and the integration is usually pretty easy. But the setup is really important. So let's go over that. Let's do a bit of concept review. When y is between 0 and 1, it's important that we notice that the sine function, sine of pi y over 2, is larger than y squared. Let's look back at the graph and see why that is. So you can see that when the sine of pi y over 2 is larger, when y is between 0 and 1, the x value corresponding to sine of pi y over 2 is larger than the x value corresponding to x equals y squared. And similarly, when y is between 1 and 2, you can see the x value corresponding to the parabola y squared is larger than the x value that corresponds to the sine function, the sine of pi y over 2. All right, so for when y is between 1 and 2, y squared, the parabola, the x value corresponding to the parabola is larger than the x value corresponding to the sine function, sine of pi y over 2. So we set up the definite integral. Area is equal to integral from 0 to 1, and it's always more minus less, x right minus x left. So that's going to be sine of pi y over 2 minus y squared dy plus integral from 1 to 2 y squared x right minus x left, y squared minus sine of pi y over 2. And this is the tricky part, is splitting it into two separate integrals for two different regions, and it has to be described differently, of course, because of the way it intersects at that point, dy. So it's always x right minus x left. Integrate, and then plus, and then the second integral is x right minus x left. All right, thanks.